Welcome to the DornerWorks American Sign Language Interpreter Senior Project Team. The main objective of this project is to create a machine learning application accelerated using a field programmable gate array, or FPGA. The goal of the machine learning application is to interpret American Sign Language in real time.
Hi, my name is Josh Johnston, and I'm a computer engineering major. My main focus on this project was the application software side of things and the FPGA HDL design.
Hi, I'm Kendra Francis. I'm a double major with CE and EE, and I mainly worked on the hardware for the project.
Hi, I'm Luke Metz. I'm an EE major, and I mainly worked on the hardware components for this project.
Hello, my name is Leah Brandaclock, and I study electrical engineering. And for this senior project, I mainly worked on the machine learning model.
I'm Grant Day. I study computer engineering. I worked a little bit with the machine learning model and also with the software side of things, and brought everything together for the final design document.
The goal of this project is to design an engaging portable demo that focuses on the acceleration capabilities of an FPGA. A custom carrier card was designed for a Xilinx SOM containing the Xilinx Ultrascale Plus MPSoC architecture, a machine learning model that we train to identify and interpret the static letters of the ASL alphabet. The model will then be accelerated using a Xilinx DPU.
At the heart of a machine learning application is a machine learning model. The machine learning model is how the computer makes decisions. An FPGA is used to accelerate the decision-making process. How does the machine learning model know which decision is the right one? Thousands of images are shown to the machine learning model in a process called training. The machine learning model can now identify key features in new images based on previous images, and make inferences as to where something is and what it is in the image. This is demonstrated in the output as a bounding box and a label.
So there were three main parts to creating a machine learning model. One is to develop a robust training data set. The next is to choose a machine learning model, a pre-existing one, and to actually train the machine learning model. The data set was one of the most important features of this project, and it took the longest to create. In total, we had 15,000 images that were labeled of letters A through Y minus J. Both J and Z require movement, which is a totally different type of machine learning. And another important feature to remember was that we had to make the data set as diverse as possible. So we had to get hand gestures in different ways. So this would be the letter A, and then we would need to change like how close it is, how to rotate it a little bit so that the model could understand, okay, well this is the letter A, but then this rotated a few degrees is also the letter A. Additionally, we had to get people of varying skin tones because the model is looking specifically for both the color, skin color, and especially the shape of the hand. So the process of actually labeling the images, we used a program called Label IMG, where we could draw a bounding box around the images, and this would then produce a set of coordinates. And then this had to be done for all 15,000 images, and then converted into a different format. Next was choosing a model. We decided to run with YOLO version 4. It's short for You Only Look Once, the fourth version of it. And now the pre-existing model means that it already came with a weight file and all the layers and nodes to connect the model or between the layers. And so all we had to do was just take that and then train it with our own data to get the model to, instead of identifying the YOLO version 4 objects from the COCO data set, to identifying hand gestures. So then the actual training portion of the model takes quite a long time. For 24 letters, it can take up to 2 days to completely train. We've been running on a 16 gigabyte GPU. It's a lot faster to train models on a graphics card than a CPU. So once the completed model was trained, we were given a weights file. We used darknet to train our model. So after that, we had to convert the model to a different format. We chose Caffe. Darknet is not supported on Xilinx products. So we convert it to Caffe, and then we have to quantize the model. What we start out with from DarkNet is called a floating point model, and we needed to change it into a discrete model, integer 8 format, so it runs a lot faster on an FPGA and makes the full use of its resources. This involved taking a couple hundred images from the training data set and then using it for quantization. Finally, the model needed to be compiled for the Deep Learning Processor Unit, or DPU, and we chose the B4096 model. That's the fastest DPU that can be run on the Korea SOM.
To understand machine learning, you first need to understand neural networks. There are two processes when it comes to neural networks: backwards propagation, used to train the network, and forwards propagation, used in the inference process. In this image, we can see there is an input layer, output layer, and multiple hidden layers. Each neuron is represented by a circle and contains a weight. Backwards propagation is exactly like it sounds. We start with the output layer and work back to the input layer. Essentially, the output and input layers are known, and the weights are adjusted in the hidden layers accordingly. This is why it is called training. Forwards propagation starts at the input layer and works towards the output layer. The input layer and the weights are known, and the output layer is predicted using that information. The weights are not adjusted during this process. Each layer takes input from the previous layer, performs calculations using the weight, and sends data to the neurons in the next layer. In this example, there are 5 inputs and 3 outputs. Let's say that the 5 inputs contain image data in the form of pixel values, and our 3 outputs are the name, size, and color of the object in the image. This requires a complex decision-making process that requires many layers of the network. A deep neural network can have just a few hidden layers to thousands of hidden layers. Now that we know about neural networks, let's look at convolutional neural networks. This is the type of network used in this project. Convolutional neural networks are specifically made for machine vision applications. Convolutions are performed on the image data before the data is run through a traditional neural network. In inferencing, the features identified during the training portion are used as filters. Filters are used in convolution layers to locate features within a pixel array and create a feature map. Pooling layers are used to smooth out feature maps by adjusting pixel values based on surrounding pixel values. After several convolutional and pooling layers, the resulting feature maps are sent through the deep neural network to be classified. The result of inferencing is an object location and a classification for an object in an image.
So for the software design side of things, there were 2 scripts that were written for this project. The first was a startup script that sets up the system for use, and the second is a main application script that runs the ASL interpreter. So the startup script is a bash script that runs automatically, and it has 3 main jobs. First, it needs to set the display resolution to match the output camera resolution to be 640 by 480. Secondly, it has to load the DPU bit stream into the FPGA so that we can use it in the inference process. And then finally, it has to launch the main ASL interpreter application script. So then the application script is a Python script that runs on the CPU, and it communicates to the DPU through the Vitis AI runtime, shortened to VART, and that API is used to talk to the DPU. So in our main application, we run through a main loop, and the first thing it does is capture an image using OpenCV from the camera, and then we convert that image from the BGR color to RGB. Then we pass that image into the DPU for inferencing, and then we wait while the DPU runs through the YOLO model, and then we get the class, location, and confidence level data from the DPU, and we draw those bounding boxes around the gesture, put the gesture description on the overlay, and we put the confidence level on that overlay. Then we display the image with the overlay, and then we repeat the process.
So for custom hardware for this project, we were tasked with designing a carrier card for a Korea SOM. So we decided to use the Korea SOM, which is a Xilinx MP-SoC. So it is a chip that has basically a couple of computer cores on it, and then also an FPGA or field programmable gate arrays, which is what this project was focused around. is doing acceleration using that FPGA. So for this chip, we have a carrier card that we designed. This here is a dev kit, so we bought this, and basically it comes with your CreaSOM, and then this plugs into this board on the outside here, so you have all your peripherals like USB, HDMI, DisplayPort, power, your SD card, and a few other things. So essentially what we had to do is we took this board, took only the parts that we were going to use, and then created our own custom board for that. So our own custom board here, all that we needed was the main connector here in the middle for our CreaSOM, which plugs right in. And then we have an SD card here on the bottom that's used for booting the board. We have JTAG over here on the side, which is used for debugging. UART on the bottom for actually communicating with the board with our computer. We have power, power for a fan, a USB port, and then a display port for driving a monitor.
This technology has many use cases in a variety of industries. In this project, we focus on American Sign Language. Communication barriers are a big issue in society, and technology, like machine learning, is helping to break down those barriers.